Welcome everyone to another session of the data learning seminars. Today we have Jacob Bieker from Open Climate Fix. He's a machine learning research engineer there, and he completed his master's in the University of Leiden in astrophysics. Jacob, thank you for doing this, and yeah, please go ahead.
Okay, yes. So I'll be talking about using AI, state-of-the-art AI for solar generation forecasts or solar PV generation forecasts. It's what Open Climate Fix is currently mostly focused on, and I've been working on for the last nearly 2 years at this point. So a bit of background on Open Climate Fix. We're a small nonprofit. There's now 7 of us, but we have a lot of different experience. One of the founders is from DeepMind. I used to work on autonomous vehicles at scale and at NASA. We have a lot of energy experience. So I worked at National Grid, which is the organization that runs the UK electricity grid, as well as a lot of other energy kind of companies. And most of our funding comes from Google.org, so the Impact Challenge, innovation funding from UK Innovate, or UKRI, and with the big contract with National Grid itself. Our whole goal is we want to maximize our climate impact as much as possible. So as part of that, everything we do is open and public. We disseminate results as quickly and in real time as we can. We've started with solar because it's, as I explain a bit later, it's the area with the biggest error for like national grids, different national grids. Solar is quite hard to predict and is quite like variable, more so than wind, for example. But we plan to expand to other renewables and other forecasting work, such as electric vehicle charging, batteries, and demand forecasting, which is forecasting the whole grid at once. Open Climate Fix was set up because the co-founders noticed a problem. The energy industry tends to be very slow moving, very risk averse. They don't want to break something and cause blackouts. And so they tend to move very slowly and have a lot of very old technology. On the other hand, you have researchers that are making really great advancements that maybe build the models, publish them, show these great results, but then don't necessarily have the time or incentive or expertise to make into a production system that would work for these kind of energy companies. And so we try to bridge the gap essentially, and try to get more like state-of-the-art research into the energy industry and try to show how you can use AI and stuff for energy forecasting and other things. So this is one of the examples of what we use and what we're trying to do. So in this video, every dot is a PV system we have live readings from around the UK. The imagery is from EUMETSAT's rapid scan service. So it takes an image of North Africa, part of the Middle East, and Europe every 5 minutes at a between 2 and 6 kilometer resolution. As you can see, when the dots are blue, they're not generating a lot, and it's yellow or red, they are generating a large portion. And as you can see in satellite imagery, you can see clouds pretty easily, and the generation matches up with where the clouds are. But this is something that's quite hard to predict, changes quite rapidly, and is essentially what we're trying to do. We're trying to predict where these clouds are going to be. And so, yeah, why we're doing this, these better solar forecasts can reduce both costs for consumers and the grid and carbon emissions. We want to reduce climate change as much as possible. And this is what we figured we can start out with. So this is from one of the people at National Grid. Embedded solar is one of the biggest sources of uncertainty. And so this uncertainty means that they need to have a lot of these big jet turbines just idling, usually at like 50%. It's really inefficient, but this thing called spinning reserve is how the grid can make sure, National Grid can make sure that if there is a big cloud over Cornwall, for example, where there's a lot of solar, and we suddenly lose a lot of solar power, the grid doesn't have blackouts, so they can ramp these up very quickly. The downside is because their uncertainty is very high in their forecasts, they have a lot of this extra generation that gets wasted, is very carbon intensive, very expensive, and very, just kind of wasteful. So giving these better forecasts can hopefully mean they can start turning off some of these backup generators and save costs and carbon. So what are we doing? We're building essentially an app that's ML powered. So this is a screenshot of in the summer our forecasting thing that the National Grid looks at. So the more yellow it is, the more solar power there is by percentage in this case. And we forecast out up to 48 hours ahead. This model is a 4-hour model. But you can kind of see where there's clouds. So it's cloudy above London and like in Scotland and such, but a bit clearer more in the middle near Birmingham and stuff. This is the same thing, just different time of day, and this is in the absolute amount of solar power. So you can see like Norwich has a lot of solar compared to Scotland, which has almost none. Yeah, so it isn't super critical to trying to get good solar forecasts, for example. And then, yeah, this is how we're getting more into how we're modeling it and the approaches we're taking so far. Still very researchy, so we're changing things a lot, but this is, yeah, essentially how we're trying to do it. Historically speaking, and currently most other solar forecasting companies and approaches use numerical weather forecasts. So these are big models of the whole world or smaller regions of the world, run on really big supercomputers. They are physically consistent, use known equations of the atmosphere, and lots, like millions of observations from aircraft and ground stations all over the world to build the state of the atmosphere and then roll it forward through time. The issue is it takes a long time to get all this data and assimilate it. It takes a very long time to run it. So these forecasts are hours, take hours to run. So they're quite stale. It's not using the most up-to-date information possible. And because they're more built for forecasting things for aircraft and ships, for example, like big storms and things like that, they're not particularly good at forecasting irradiance. So how much solar, how much sunlight's actually hitting the ground at any point, or at resolving clouds. Part of it is that most of these big models are not high resolution enough to really model clouds very well. On the other hand, you have a lot of these emerging approaches from like AI and machine learning that are data-driven. You can take in new types of data, so the satellites and live readings from PV panels on the ground. They're very fast to execute. We do new forecasts at least every 5 minutes and sometimes more often. And there's a lot of information, a lot of geophysical information that we can take in to these models. And like at this point, decades or years to decades of historical data that we can train on. So we have a lot of training data, which is very good for all these ML models. How most of our models work with what we're doing is we combine the very multimodal inputs to output different types of solar PV forecasting. What the main one is actual live readings from panels on the ground. That's probably the most important input. We also then include the numerical weather predictions. So we, especially for forecasts out like to the next day, we need these numerical weather models to give a good like estimate of the temperature and things like that. Live satellite imagery from, as I showed in the video, that's every 5 minutes. And then topographic data, so like where mountains are and different elevations that might affect shading and things like that on individual panels. So all these go into one of our different ML models, which I can go into detail a bit later. And we ideally get improved solar generation forecast compared to what National Grid has. So currently we forecast both nationally, regionally, there's 317 regions that we predict for in the UK, and for individual sites, so individual solar farms or like household solar panels. Here's a few different ways that we've been trying it out. So a lot of these models are based off of other state-of-the-art models and adapted to what we're trying to do. So this one is skillful nowcasting GAN, which is built by DeepMind for predicting precipitation, rainfall basically, and like flooding. It's a GAN and takes the last 20 minutes of rainfall radar and predicts the next hour and a half. So quite short term. Had pretty good results. They did a lot of different studies and stuff on showing that it worked well for meteorologists. So like this output wouldn't go directly into predicting exactly where rainfall is going to be, but be given to a meteorologist, which then helps interpret the results. We modified to take multi-channel images and to output satellite imagery or individual PV yield as well. One that's also similar, this one's from a lot of the Google models. This one's from Google Research. It's called MetNet and MetNet 2, which also designed to forecast rainfall. This one was done with trained over the US, and yeah, it's kind of works out shown here. We adapted it to work with more multi-channel images and more data inputs. I have been using it to try to do it for our national forecast. This is more of a baseline model that we have. So it's a 3D convolutional model. So this one's quite simple. It just takes satellite imagery and the numerical weather data, puts it through normal standard 3D convolutional models, and then some fully connected layers, and includes some PV history. It works actually pretty well, a lot better than the current National Grid ones. It's very simple to run, very simple to train, and is actually a decently strong baseline. And this is one of our more researchy ones that we've been doing. So besides just trying to predict the actual amount of PV power you can have at any given point, another useful thing is try to predict like probabilistic forecasts. So not just how much you think it'll be, but what's how likely it's going to be in this range for this planning purposes for National Grid. So we're trying to incorporate different probabilistic outputs as well. And this is based off a model from DeepMind called Perceiver or Perceiver and Perceiver.io, which can take multimodal inputs, compresses those into a latent space and runs the transformer like cross attention over it, and then it can output multiple different outputs. In our case, we'd use it to output a probabilistic PV forecast. In our results, we have this is the current National Grid's current model, which is roughly a 10% error regionally and around 8.5 to 9% nationally. The PVNet is that convolutional 3D model, so it's already like a few percent better and a couple hundred megawatts better than the National Grid's model. Regionally and nationally, it's around half the error. And then our power perceiver is that one I just showed you based off Perceiver.io. That is around 3 times better than the National Grid's model. We also have some newer ones that just aren't on here. Essentially just kind of showing that even with very simple models, you can do much better on these solar forecasts. And then with the more state-of-the-art ones, you can do quite a bit better on top of that. And we're hoping to keep improving as time goes on. We also done a bit of an ablation study. This is on the PVNet, so the convolutional 3D model, and training just various permutations of different inputs to try to figure out what drives accuracy the most. As can be expected, live readings from PV panels on the ground drives most of it. So if you're getting like actual history of what you're trying to predict, that obviously helps quite a lot. Solar geometry is where the sun is in the sky. So how high is it? And so then the model can learn how to go from that to how much it's hitting the panel directly on like a clear sky. Then you also have the weather forecast and satellite imagery. So the weather forecasts provide, this weather forecasting satellite imagery are part of what we call the Earth observation data. So the data from observing the Earth and the weather models and things like that. The weather forecasts provide a good chunk of it, but the satellite imagery is about 40% of that Earth observation contribution, which is a pretty good chunk and actually provides a really nice bump in accuracy compared to just relying on the weather data. This does drop as we go further into the future. Like if you're predicting for tomorrow and not the next, in this case, like 4 hours, satellite like satellite images don't matter too much because they're very far out of date, versus the weather forecast can at least move through time to that future time period. So we'd expect it to go to nothing. Our estimate is around 12 hours into the future, but we're still investigating that some more. Open Climate is also working to try to maximize our impact. So beyond doing this research, using it in our products, things like that, we have a whole thing about lots of open data, open models, and open research. So all of our training data, as much as we can make publicly available, is available on Hugging Face and Google Public Datasets. So it's very low barrier to entry. So anyone can go there and grab all of it and do it. The only limitations we have are for specific like location information for some of the panels we have data for, because that's like private information, or the Met Office. We use some of the Met Office's weather models and they don't allow redistribution. All our training code and model weights are released also on Hugging Face, but also our training code is on GitHub. All our production pipeline is public, so how we go from the raw data to putting into our model is there. We try to make everything easy to like pip install, and it's designed to be extended easily. And all of our developments in the open. All our research ideas we put on GitHub, and all our results we put on GitHub issues and such in real time as we do with it. A bit more detail on the open data is we have tens of terabytes of weather data in easy to use formats, primarily ZAR, and built with Xarray, if any of you guys have used it. We've also have multiple years of UK PV data, one of the largest that we know of, one of the largest data sets of like live PV readings in the world. We have 8 years of European satellite imagery at 5-minute intervals. We're expanding it to around 10 or 11 years right now. Then we have multiple years of US, Swedish, and UK precipitation radar data. We don't currently use in our models, but we want to in the future. And it's partly from people working with us and use our models for other rain forecasting, and then having us share their data that they're using to train with. We also have the code that we use to collect all this data and convert it to these formats that are easy to use and train with. We also have lots of pre-trained solar forecasting models publicly available. We implemented models from state-of-the-art papers, especially where the paper authors didn't make their code public. And we've tried to collate and release matching or similar data sets to those in the papers to try to help with reproducibility, along with our flexible training pipelines. And then the last bit of open research, we do all of our research progresses in the open. We've done hackathons. So one was Climate Hack AI, which was run primarily by students at UCL, involved, I think, 25 universities around the world, like Stanford, I think Imperial as well, trying to predict one part of our problem, trying to predict future satellite imagery. And our whole thing is we want anyone to participate. We've co-supervised bachelor's, master's, and PhD projects at UCL, Edinburgh, various other ones. I'll be co-supervising some with Cesar here at Imperial. And we're doing a lot of current research. So more PV models, graph neural networks, and diffusion models for weather forecasts, and pseudo-labeling PV data. So I'll get into a little bit more. So for what we're like currently working on, one is combining some newer Google Research and DeepMind models, so hierarchical perceivers and MetNet version 2, to have a more efficient and better forecasting model for solar. We just have a few graph neural networks for trying to predict future weather. So this was originally based off a guy's paper in 2022, but use a graph neural network to forecast global weather. And in our case, we would use it to create large ensembles of weather forecasts, so like thousands of members, and use that to help with forecasting, with making our models more probabilistic. versus the more deterministic NWP outputs that we currently use. This is another one that just came out, actually, I think is, or in December, GraphCast, which is built on the previous graph model, and is one of the project ideas we have to extend our thing to copy this, and extend it more to what we want as well. Another one that we're working on that I'm going to be starting soon is pseudo labeling the PV data. This idea originally came from OpenAI for a model they made to play Minecraft. They created a model that, they had contracted to produce 2,000 hours of labeled videos, and then use that to train a model to predict actions given past the future frames. So cheating into the future, which you wouldn't have in production, but you can for these training data sets. And then they took 70,000 hours from YouTube of the same things and had it label those before then training another model on the pseudo labeled data and real labeled data combined, which had a much better performance than one just trained on the contractor produced data. So our plan is to try to do that for solar forecasting. So we have around 25,000 PV sites that we have data from, and we are planning on building a model to do the same thing, predict the output based off the future and past satellite frames and other things around it, and then label the 10 years of satellite data that we have, and every single pixel within that satellite data. So we have millions of more training examples that we can train our models on, which we are pretty sure will improve the performance. But as with all research, we need to find out. The end result for it kind of things is that we have very easy to use forecasts updated in real time. The output is designed to be user-friendly and easy to understand. And so the National Grid users don't need to know how the machine learning works or programming or anything like that. They can just see what our thing is forecasting. We also have very engaged users that are, we have a lot of like one-on-one talks with them and like constantly make sure our approach works well for them. We have external contributors in our GitHub, around 70 last we checked, that have helped with pointing out bugs, doing fixes, extending our models to other use cases, things like that. And our idea is that the open approach guarantees the continuous improvement in our models, our forecasting, and in other things as well, and our research to make it as best as we can be, to have the biggest impact that we can possibly have. So yes, that's all I have to say for now, but open to any questions or anything else.
Thank you, Jacob. That was very thorough about the work you guys are doing. You have any questions for Jacob, just type them on the chat, or you can raise your hand and So any questions? I can start in the meantime. With the solar PV maps, you mentioned what's the resolution of the cloud covering again? Sorry, if you mentioned.
Yeah. So the cloud cover is where is the, there we go. For this, the satellite imagery has a resolution of between 3 and 9 kilometers per pixel. There's one high resolution channel, which is 3 kilometers, and 11 which are lower, which is 9 kilometers. It also changes. So like in Scotland, each pixel is about twice as tall as it is wide on the ground. But in Cornwall, it's more square. So it's somewhat challenging to work with. But
all right, is that problem with the sorry? Is that an issue with the latitude of the data, or just
because it's all geosynchronous satellites, and so it's just the Earth's curving away from it, and so the pixels are the same shape, but on the ground it's elongated.
And you think like you have 3 to 9 kilometer resolution? Do you think I don't know if you manage to do some kind of like downscaling to 1 kilometer, will that add a lot more to the prediction that you already have with the National Grid?
For National Grid, probably not as much because it's more like we're looking at the bigger regions and things like that. But when we're doing site level stuff, it become quite important. They did on December 13th, they launched a new generation of satellites, which doubles or the spatial resolution doubles. So that would help more with like site level forecast. So forecasting for any of these individual points. But I don't think probably as much for the whole national bit.
Yeah, okay. And so for example, what these products are you working? Is it like the satellite images? So when you don't have clouds, there's like you can assume it's no data there. Will it be assume it's like a sparse data set?
No, so we don't actually segment out the clouds. It's still so like what the model's getting is what you're seeing in this. So you just see the ground as well. So that does have to learn what's the ground and what's the clouds. But
all right, okay.
Yeah.
Yeah, because I was thinking of like sparse data sets if like you have encountered them in this application, maybe like another application you're working on, and how do you deal with them?
It hasn't been many sparse data sets that we've worked on. There's been some dealing with like the precipitation radar data. There's a lot of just like no data in between things. And the way I've seen people do that in some of the data sets we've worked with is do like weighted sampling. So you make sure, like for especially rainfall, when you have like a few very severe events and a lot of nothing, make sure it's more balanced, so that the model doesn't just learn to always predict nothing. So that's what we mostly learned around that. For this, we do have some like specific dates and stuff where the National Grid's forecast was off by a lot. And so we do look at those specifically. Just make sure like essentially that our models wouldn't have done that or would have been off by that much. But that's more cherry picking examples than I guess sparse data set.
Yep, cool. Rosella, do you have a question?
Yeah, actually, I have a more, let's say, general question. I was wondering a couple of stuff. Like the first is, so first of all, thank you for the presentation. It gave me like lots of thoughts and very nice input. I was wondering, how long did you test your system in terms of forecasting? So I know this is now casting. Do you think this can go like a bit further in the future? And also, in order to, let's say, overcome the limitations of the existing operational codes, how do you think your system can, for example, increase the resolution or anyway improve the reliability of the existing operational systems, like coupling with them or stuff like that?
So for for trying to like deal with like reliability issues and things, is actually one big thing is this 5-minute service that we use for this shuts off for a month every year, and 48 hours every 26 days. So we just have to build a lot of like backup satellites that we get data from instead, and train it on 15-minute data, which is the backup data versus normal one. We have tried to do things like super resolution, but because the geostationary satellites don't move as much, it doesn't work as well as with some like lower satellite imagery. We currently, the resolution seems to work well enough for what we're doing, and the limitations for us is more on the side of we can't get enough like PV data. More PV data is easily correlated, like it's like very correlated to our models doing a lot better. And the biggest problem is a lot of companies that have like PV generation data don't want to give it to anyone. So like to prove the reliability more or to have better forecasts, more data is always better. But I think the biggest is just getting more live readings. Part of the things I forgot to mention on this is that like in the UK, we have one of the better systems of tracking where PV is installed, but we still don't know where around 5 to 10% of it is. Like we just have no clue where the panels are or how much they generate. And that leads to a decent amount of uncertainty. If you don't know where the panels are that you're trying to forecast for, it's obviously hard to forecast for them. But that getting better at that is like, yeah, trying to either map things from satellites, which is something we are trying to do, or like regulatory changes, which is something we don't really deal with, but is part of more better way of fixing it. Yeah,
I see.
I forgot your first question. Could you repeat it?
No, the first question was more about for how long do you think the system
Oh, yes.
will be able to forecast without like crashing, let's say, in terms of accuracy, obviously.
Yeah, I would think so. I think it could go out quite far. So I think our models could go out to like a week ahead if you really wanted to. Beyond like all the stuff we're caring about essentially is the next 48 hours. There's like a few different teams within National Grid that like schedule different generators and stuff, and 48 hours is the limit for one of the teams that we work with. And so that's the one we care about the most. It's still like nowcasting-ish. But even at that point, our models, essentially the inputs aren't useful except for the NWP data. And so I would think you can just keep going out as long as the NWP data is there. They're just essentially the performance will just drop to like other solar forecasting companies' performances, which they primarily just use the numerical weather data anyway. So it'd be much better early for the first couple hours or 12 hours or so, and then it will drop down over time to what their performance is.
Yeah. So it will be very interesting checking the potential of these models to overcome what the NWP models are able to provide now. So
Yeah.
I heard some, like for example, there are some of the operational centers, not in the UK, but in Japan, for example, they are completely running part of the tools on using AI instead of, so like they are replacing the standard NWP model.
Oh yeah.
Yeah. Just wondering if, we are in the same direction, but probably we will see this slowly.
Yeah, there was. So I was at ECMWF conference a while ago where they said they're starting to use neural networks. They have a 4chan neural network library for some bits of it. So but their main concern seemed to be making sure it's still physically consistent because neural networks aren't always the best at those constraints. So yeah, I mean, I think for like our forecasting, where I mean, obviously it's better the more physically consistent it is, but it would probably okay if it's not perfect. Doing these like graph neural network forecasting models, I think, would be a good way where we can either augment the actual ones from like the Met Office or replace them to some extent with as inputs, and use these very fast, very quick, consistent enough models, I guess, for as inputs. But yeah, at least that's kind of my hope, because yeah.
No, absolutely. I completely agree with you, and thank you very much again for the amazing presentation.
Yeah.
Can I ask another question? You're showing here like the UK. Do you have any plans for the company of like for research wise to extend to other areas, or do some kind of validation in other regions?
Yeah. So we are currently doing a pilot for a company doing site level forecasts in Italy. We're in talks with some some people in the Netherlands to do it there, and in India as well. So we want to do it as much as we can. The focus for the UK so far is the UK has a lot more information on all these other places about their energy grid that we can access. Also, we're based in London, so it's a bit easier to work with the national grid versus other places. But yeah, we are planning on doing it other places. Our data, the types of data we use is mostly available globally, quite easily. And so like if our models work for the UK and we can validate it there, we should be able to retrain it or fine tune it for different areas, but should then work pretty easily out of the box.
Yep, cool. Yeah, sounds like a great vision. Anyone have any other questions for Jacob? Nope. I have one more question. For example, you show like GraphCast, which was released just in December. Yeah. So if you guys planning to implement this, as try to implement it in like a more local scale.
Yeah, we want to, because this seems to work better than the last one and builds off the same idea as the previous one, the other graph weather one. So we'd like to, and we have plans to do it. Yeah, it's currently we have some other things. I haven't had as much time to work on this, but we try to incorporate the newest and greatest models as soon as we can on the stuff we're doing. So yeah,
I mean, just came out like a month ago. So
yeah. So we'll this one we got a model mostly working, I think 2 months after it got released. So this will probably be a bit longer, but hopefully soon as well, because they haven't released I don't think they're planning on releasing the model either for this one. So yeah, we'd like to get some implementation out.
Yeah. Okay. Yeah. Cool. I mean, all of this sounds super, like, so sounds amazing, really. And I feel like I know the community working on this weather prediction with machine learning is not as big as one will expect at the moment. So I think it's like good. It's a good space to take advantage of other methods and try to apply them on. I mean, it could be anything really, like rainfall, like temperature, like the solar PV as well. Seems like a wide range of applications.
Yeah, or like wind forecasting. There's I mean, weather feeds into so many other things that getting better forecasts has a lot of applications as well.
Yeah, no, it looks super good. If there's no more questions, I think we can leave the talk up to here, and then we can say thank you, Jacob, for your time and sharing your work with everyone. And thank you so much for attending the meetings today.
Yeah, thanks for having me.
Yep. Bye, everyone. Have a good day.
Thank you. Bye.
Thank you. Bye.